Hello and welcome to Control Systems Lectures. In our previous lecture, we saw that control system design depends on three specifications. Transient response, which deals with the rise time, settling time, and percentage overshoot. Stability, which deals with the characteristic of the system to converge and settle at the input command or diverge and be unstable. Finally, the last specification is the steady state error. We covered the first two specifications in our previous lectures, and in this lecture, we will be considering the steady state errors. On the stability, we observe that the force response is overpowered by the natural response increasing without bounds in an unstable situation. We will now look at the steady state error of control systems. The learning outcomes, therefore, for this lecture are: 1. You will be able to find the steady state error for a unity feedback system. 2. Specify a system's steady state error performance. And 3. Design the gain of a closed loop system to meet a steady state error. Specification. This lecture is based on chapter 7 of your textbook. First, we will define the errors and then develop methods of controlling them. In subsequent lectures, you will discover that control system design is usually a trade-off between desired transient response, steady state error, and the stability requirement. As a way of definition, the steady state error is the difference between the input R of S and the output C of S for a prescribed test signal as time goes to infinity. In this slide, I would like to introduce these test signals. Some will be familiar to you already. A step input is a constant position with a time function of 1 and Laplace transform of 1 over S. It is useful for testing the ability of a control system to position itself with respect to a stationary target. Next is the ramp input with a time function of t and Laplace transformed to 1 over s squared. The ramp represents constant velocity inputs to a position control system by their linearly increasing amplitude. This test signal can be used to track a constant velocity target. And then finally is the parabola input with a time function of 1 half t squared and Laplace transformed as 1 over s to the power 3. The parabola represents constant acceleration inputs to a position control system. This can be used to represent accelerating targets, for an example, a missile. Let us now evaluate the steady state errors. However, take note that before analyzing a system for steady state error, the system must be stable. Otherwise, the results will not be useful. In figure A, we have a step input and two possible outputs. As you can see, output 1 has 0 steady state error, since its final value equals the input. However, output 2 has a finite steady state error. A similar comparison is done in figure B using the ramp signal, in which output 1 has 0 error and output 2 has a constant finite steady state error. On the other hand, output 3 has a slope that is different from that of the input. Hence, the steady state error will keep widening non-stop. Hence, the steady state error is infinite. Keep this in mind as we proceed with the evaluation of the steady state error. So you can either have a 0 steady state error, a finite steady state error, or an infinite steady state error. Before we derive the steady state error for a unity feedback system, let us first consider the sources of steady state errors. Many steady state errors are due to nonlinear sources like backlash in gears or motors. But in this course, however, we are dealing with linear systems. Therefore, the steady state error we will be considering are due to the configuration of the system itself and the type of the applied input. For example, consider this figure where R of S is the input, C of S is the output, and the error is given by E of S, which is equal to the difference between the input and the output. Let us consider a step input. If the C of t is equal to R of t, then our error signal E of t will be 0. But with the pure gain k, the error signal cannot be 0 if C of t is finite and non-zero. We can then see that due to the gain k in the system, a steady state error will exist. If C of the steady state is the steady state value of the output and E subscript steady state is the steady state value of the error, then C subscript SS is equals to K multiplied by E subscript SS in the time domain, or the steady state error E subscript SS of T is equals to 1 over K multiplied by C subscript SS. Therefore, the larger the value of K, the smaller the steady state error. Our conclusion, therefore, is that with a pure gain in the feed-forward path, there will always be a steady state error for a step input. This error diminishes with increasing value of K, and we'll come back to this later. If we now have an integrator in the feed-forward path, there will be a 0 error in the steady state for a step input. Let me explain this. As C of t increases, E of t will decrease. Since E of t is equal to R of t minus C of t, E of t will eventually become 0. However, C of t will still have a value since an integrator can have a constant output without any input. An example is when we apply a voltage to a motor. It will cause it to rotate. After the voltage is removed, the motor will stop rotating and it will remain at its present output position. Since the motor does not return to its original position, we have an angular displacement output without an input to the motor. The steady state error can be calculated either from the system's closed loop transfer function T of S or from the open loop transfer function G of S for unity feedback systems. We will illustrate both methods. First, let us consider the steady state error due to the closed loop transfer function T of S. From this figure, we can see that the error E of S between the input R of S and the output C of S is given by equation 7.1. But we also know that C of S is equal to R of S T of S using our block diagram algebra, which is the equation 7.2. If we substitute equation 7.2 into 7.1 and simplify, we have E of S is equal to R of S, and then in the bracket we have 1 minus T of S. This is the error due to the transfer function of the system T of S. With equation 7.3, we can compute the error at any time t. However, since we are interested in the steady state error, which is as time goes to infinity, we will then apply the final value theorem to 7.3. This will give E infinity, which is as time goes to infinity, is equals to the limit as time goes to infinity of E of t, which is equals to limit as s goes to 0, s E of s. This is the final value theorem equation. Let this equation be 7.4. If we substitute equation 7.3 into 7.4, we arrive at E steady state, which is at infinity, is equals to limit as s tends to 0, s R of s, bracket open, 1 minus T of s. Let's call this equation 7.5. We will now demonstrate the use of equation 7.5 with an example. In this example, we are to find a steady state error for the system whose closed loop transfer function T of S is given by the equation T of S is equal to 5 over S squared plus 7S plus 10. And the input is a unit step. We are to assume that the system is stable. Since we are told that the system is stable, we do not have to check for stability. Hence, we will apply equation 7.3 straight away by substituting for T of S and the input signal, which is 1 over S. Taking the limits as S tends to 0 will give us a finite steady state error of 1 over 2 or 0.5. Now let us show how you can compute the steady state error using the feed-forward transfer function, which is the G of S. The advantage of using the G of S for a unity feedback system to compute the steady state error is that we gain more insight into the analysis and design of the system. Now consider the unity feedback system in this figure. The error signal will be given by E of S is equal to R of S minus C of S. From the diagram, we also know that the output signal is given by C of S, which is equal to E of S G of S. If we substitute equation 7.7 into 7.6, we will arrive at equation 7.8. Now we can use the final value theorem to find the expression for the steady state error, which is given by equation 7.9. Equation 7.9 then allows us to calculate the steady state error given the inputs R of S and expressing the relation between the open loop transfer system, which is G of S, transfer function, which is G of S, and the type of steady state error. Let us start with a step input. Using equation 7.9 and substituting R of S equals to 1 over S, which is unit step, and taking the limit as S tends to 0, we will have the expression 1 over 1 plus limit as S tends to 0 of G of S, where the term limit as S tends to 0 G of S is referred to as the DC gain of the system. In order to have a zero steady state error, the limit as S tends to 0 G of S must be equals to infinity, making the denominator very large, and hence the error signal will tend to 0. In order to satisfy the condition indicated in equation 7.10, the G of S must take the form of equation 7.11, where the Z's and the zeros and the P's are the poles. For this equation to become infinite, the denominator must be equal to 0 as S tends to 0. Therefore, n must be greater than or equals to 1. This means that there should be at least one pole at the origin. Since 1 over S is an integrator, it means that we should have one pure integrator in the forward path. In the fourth path. If n, on the other hand, is equals to 0, which means we do not have an integrator in the forward path, our limit as S tends to 0 will give us G of S equals to Z1, Z2 over P1, P2, and so on and so forth, which implies that we will have a finite steady state error. This is summarized in this table and illustrated in the figure. For n greater than or equals to 1, we have output 1 with 0 steady state error. And for n equals to 0, we have output 2 with constant finite steady state error. We proceed in the same fashion for the other test signals. For the ramp input, therefore, we substitute R of S equals to 1 over S squared. Substituting this into equation 7.9 yields equation 7.13. To have a zero steady state error, therefore, the limit as S tends to 0, Sg of S must be equals to infinity. And to satisfy equation 7.11, n must be greater than or equals to 2. This means that there should be at least 2 integrators in the fourth path. If there is one integrator, there will be a finite steady state error. This is shown in the table and illustrated in this figure, where output 1 is the case where we have at least 2 integrators in the forward path, and hence we have 0 steady state error. And output 2 is the case where we have 1 integrator in the forward path, and hence yielding a finite error or a constant error output. And the third output is the case where there is no integrator in the fourth path, hence we have infinite error leading to a divergent RAM output. We proceed in the same fashion also for the parabolic input, which is a constant acceleration test signal. Therefore, we substitute R of S, which is equals to 1 over S to the power 3, into equation 7.9 again, yielding equation 7.15. To have a 0 steady state error, therefore, limit as S tends to 0 of S squared G of S must be equals to infinity, where G of S is equivalent to equation 7.11. To satisfy equation 7.11, N must be greater than or equals to 3. This means that there should be at least 3 integrators in the forward path. If we have 2 integrators, there will be a finite steady state error. If there is only 1 or less integrator in the forward path, then our limit as S tends to 0 will be 0, and the steady state error will be infinite. Let us now use an example to illustrate what we have learned. In this example, we are to find the steady state error for the input U of t, 5t u of t, and 5t square u of t for the system shown. The function u of t is the step, is the unit step input. All right, step 1. Verify that the system is stable. I'm not going to do that here, but this is what you do. First, you find your T of S, which will give you 120 S plus 2 over S plus 3, S plus 4, plus 120, S plus 2. If you open all this bracket, and then you use your Ruth table, then you can verify for stability. So I'll leave this to you to complete this, just to verify that the system is stable. Also note that your 5 u of t, if you Laplace transform this, it will give you 5 over s, and your 5t u of t, if you Laplace transform this, let's put Laplace transform this, it will give you 5 over s squared. This is for the RAM. This is for step. So this is step, this is RAM. And then for your 5t square u of t, if you Laplace transform this, it will give you 5 over a half s to the power 3, which will be equals to 10 over s to the power 3, and this is here parabolic function. Okay, so now we're going to find the steady state error. First, for the step steady state error, remember this will now then be 5 instead of 1. It will be 5 over 1 plus limit as s tends to 0 g of s, which is equals to 5 over 1 plus limit s tends to 0 of 120 s plus 2 over s plus 3 s plus 4. So this will give us, this will be equals to 5 over 1 plus 20, which is equals to 5 over 21. So which implies that a response similar to our output 2 of the figure, where there is a constant steady state error, is what we have here. Now we go for the second one for the RAM input, which consists of ERAM. So for the ERAM, this will be equals to 5 over limit as s tends to 0 s g of s, and so this will be equals to 5 over limit as s tends to 0 s, here we have 120 s plus 2 over s plus 3 s plus 4. This will give us 5 over 0. As s tends to 0, this becomes 0, so this whole thing becomes 0, and so this is infinity, which implies an infinite output. So this is infinite output, and so we have a finite output, finite steady state, and here we have infinite steady state. Next, we then find the parabola steady state error. So this will give us 5. Now remember our R of S. So let me remember that we said that when our R of S for the parabola was actually 10 over S cubed. So E parabola steady state will be 10 over limit as S tends to 0 S square G of S. So if you substitute that, that would be 10 over limit S tends to 0 S square, and here you have your G of S, which is 120, again S plus 2 over S plus 3 S plus 4. Of course, this will be 0, and so this will be 10 over 0, which is also infinite situation. So we have infinite steady state error. So these are the results, and you can see from the problem that because we have our n is n to the power 0, which means we don't have any pure integrator in the forward path here. Because of that, you're going to have a finite step, an infinite RAM, and an infinite parabolic. Okay, this is example 7.3 in your textbook. 7.3, you'll find this on page 348 of your textbook. It's the same question. We are to also find the steady state errors for inputs 5ut, 5t ut, and 5t square ut. So we already know the Laplace transform of all these inputs of these inputs. This is step input, and this is a RAM input, and this is a parabola input. So this is the system we have now, and so our g of s is now this quantity here. Now you can see that we've got at least one pure integrator in the forward part of the loop. This tells me that the RAM function will be finite and that the step will be 0 steady state and the parabola will be infinite. But let's show this. So now we start with our so let's start with the step. So E step is equals to now we have 5 over 1 plus limit as s tends to 0 g of s. So now this will be equals to 5 over 1 plus, so limit as s tends to g of s, we have 100 there, s plus 2, s plus 6 over s, s plus 3, s plus 4. So you can see that because s is 0 here, the denominator of this is 0, so this function is actually infinity. So this will give us 5 over infinity, which is equals to 0. So we have a steady state error for the step to be 0. Next, we look at the steady step for the RAM input. So we have the RAM input. This will be 5 over limit as s tends to 0 s g of s. So you can see this will be equals to 5 over 1 plus, so 100 s plus 2 s plus 6 all over s. So now remember we have this s here, so we have s plus 3, s plus 4. So this will cancel out, and if you substitute the 0 here, this will give you 5 over 100, so which is 1 over 20. So we have a finite, so this is 0 steady state error, and here we have a finite steady state error, just like we predicted. So now we check the parabola. So for the parabola, we say E parabola steady state error parabola. This is equals to
10 over limit as s tends to 0 s square g of s. So this will be 10 over limit s tends to 0. So we have s square, and then g of s is 100, s plus 2, s plus 6 over s plus 3, s plus 4. So you can see this s cancel, and that we left s there, and this becomes 0. So this will now be equals to 10 over 0, which gives us an infinite steady state error. So this is the second example. What we can summarize from here is, if you look at this question, is got a pure integrator, and because there is a pure integrator in the denominator of the g of s, this in the forward part of the system, if n is equals to 1, then we'll have a finite RAM. If we now have another example with s here being s square, it means that the step will be 0, the RAM will be 0, and the parabola will be finite. So that is one way to be able to predict the steady state error before you even start to calculate it. And we're going to then use this power of the integrator here of the denominator in the next lecture to describe what we refer to as system type. So we'll name the type of systems based on the power of this denominator of the g of s, or if you like, the integrator, pure integrator or integrators on the forward part of the loop.
Welcome to Control Systems lectures. In our last lecture, we derived the equations for the calculations of steady-state errors for a unity feedback system. We saw how different input signals can be used to analyze different position control scenarios. Continuing with the unity feedback system, we will define parameters that we can use as steady-state error performance specifications. These specifications will parallel our definition of damping ratio, natural frequency, settling time, percentage overshoot for the transient response specifications. These steady-state error parameters specifications are called static error constants. At the end of this lecture, therefore, you will be able to 1. Specify a system's steady-state error performance, and 2. Design the gain of a closed-loop system to meet a steady-state error specification. In the last lecture, we derived the following relations for steady-state error. The first one, for step input, the steady-state error is given as 1 over 1 plus limit as s tends to 0 of g of s. And then 2, for the RAM input, the steady-state error is given as 1 over limit as s tends to 0 s g of s. And for the parabolic input, the steady-state error is 1 over limit as s tends to 0 of s square g of s. The limits of the terms in the denominator determine the steady-state error. We call these limits static error constants. And individually, these are the position constant, which is Kp, where Kp is the limit as s tends to 0, g of s. The velocity constant, K subscript v, where K subscript v is the limit as s tends to 0 of s, g of s. And the acceleration constant, K subscript a, where k subscript a is limit as s tends to 0 of s squared g of s. From these equations, we can see that the steady state error decreases as the static error constant increases. We can also use the static error constant to compute the steady state error as an alternative to using the final value theorem. We will use an example to illustrate this. In this question, we are to evaluate the static error constants and find the expected error for standard step, ramp, and parabolic inputs for this system. In order to solve this, you must first verify if the system is stable. I have confirmed that it is stable, but I'm not showing this here. So next you compute the static constants. Therefore, our g of s, which is equals to 500 s plus 2, s plus 5 over s plus 8, s plus 10, s plus 12, and we compute our static error constant to yield kp will give us 5.208, our kv will be equals to 0, and our ka is also equals to 0. Therefore, the steady state errors are 0.161 for step input, which is a finite error, and infinite error for both ramp and parabolic inputs. Let us consider another example. In this example, we are to also evaluate the static error constants and find the expected error for standard step, ramp, and parabolic inputs for this system. It has been confirmed that the system is stable, therefore we will skip that here. Also notice that we have at least one pure integrator in the feed-forward path. This immediately tells me that I will have 0 steady-state error for the step input, but let us show how. Next, you compute the static constants. Our g of s is equals to 500 s plus 2, s plus 5, s plus 6 over s, s plus 8, s plus 10, s plus 12. And we compute our static error constant to yield kp equals to infinity, kv equals to 31.25, and ka is equals to 0. Therefore, the steady state errors computed as 0 for step input, as we predicted, because we have one integrator in the feed-forward path. We have a finite steady state error for the ramp input and an infinite steady state error for the parabolic input. We are still focusing our attention on the unity negative feedback system. And now we will explain system types and the steady state specifications. We have shown that the static error constant depends on our g of s, especially on the number of pure integrators in the forward path. Since the steady state error depends on the number of integrators in the forward path, this has been used to name the system type. If we consider the generic unity negative feedback system in this figure, we define system type to be the value of n in the denominator. Therefore, if n is equals to 0, we will have a type 0 system. For n equals to 1, we have a type 1 system. And for n equals to 2, we have a type 2 system. This table ties up the concept of steady state error, static error constant, and system type. The table shows the characteristic of the system types. Please take some time to study this table and to understand the various components. The static error constants can be used to specify the steady state error characteristics of control systems. For example, steady state error is an important design consideration for assembling line robots, just as we use the damping ratio settling time, peak time, and percentage overshoots as specifications for a control system transient response. In the same light, we use the position constant kp, velocity constant k subscript v, and acceleration constant k subscript a as specifications for the system's steady state error. For example, if a control system has the specification K subscript V equals to 1000, we can draw several conclusions, which include the following. One, the system is stable, because usually the system must be stable before we can compute the static error constants. Two, the system is of type 1, because it's KV. Three, a RAM input is the test signal. And four, the steady state error between input RAM and output RAM is 1 over KV per unit of the input slope. Now, let us consider the specifications Kp equals to 100. What information can we get from this specification? Try answering it before looking at the results, which is in the next slide. Well, if you get the following information, congratulations. In this next example, we will use the steady state error concept to design a control system. Let's say you have the following control system and you have been asked to find the value of the gain K of the system so that there is 10% error in the steady state. From the forward path, we have G of S is equals to K, S plus 5 over S, S plus 6, S plus 7, and S plus 8. We can see that in this case, N is equals to 1, which means it is a type 1 system. Therefore, the error stated in the problem must apply to RAM input only, because only a RAM can yield a finite error in a type 1 system. Therefore, steady state error will be given by 1 over K subscript V. Since the steady state error must be 10% according to the question, substituting this into the equation and simplifying as shown here yields K is equals to 672 or 672. If we substitute the K value into the system and carry out the stability analysis using the Routh-Hurwitz method, we will see that the system is stable. On the other hand, we could write a simple MATLAB code with K equals to 672. If you run this code, it will yield the closed loop transfer function T of S and also generate the poles. And since all the poles lie on the left half of the S-plane, we conclude that the system is stable. You can see that in this example, two design specifications have been met, namely the steady state requirement and the stability requirement. However, this does not imply that the desired transient response has been met. We will show how to design feedback control system to meet all three specifications in subsequent lectures.